So next speaker, Atkinson, adaptive design for clinical trials that maximize utility.
Well, thank you very much. It's a long time since I last gave a talk in Cambridge. Right. Oh, sorry, yeah. As you will find out, I got rather carried away when doing the work for this talk, and unfortunately there isn't very much about utility, but I hope nonetheless it is still interesting. There's the LSE logo. This is what's going on, what I'm talking about. So we have a lot of patients coming along sequentially. Each one, as he or she arrives, is given one of T treatments. They arrive with the vector prognostic factors, and we're interested in well, probably selecting the best treatment. We might also want to estimate a treatment effect, and the responses on patients before the eye may be available. Do you think so?
Like.
Well, I don't know. Okay, I have to, it's all right. So the idea of adaptation will be to treat more frequently with a better or best treatment. One also wants some kind of balance across these prognostic factors. Ideally, all kinds of patients should get all kinds of treatments. There needs to be some randomization, some claim to objectivity, avoidance of conscious or unconscious biases. David Cox mentioned this a bit. And in a non-clinical context, there is a Lanarkshire milk experiment, which is an example of what can happen if you randomize and then perturb things, I think. Now that's the other thing I wanted to say that I haven't put up there is I will be talking about designs for 200 patients or something, but they're not. We don't know when we're going to stop. We may stop at 37 patients or 48 or something. So one wants a design that has good properties, in particular is reasonably balanced for the whole range of values of n, not just the particular n you will find me talking about. I'm going to assume that the data are going to be analyzed with a linear model. These are what we're interested in, the treatment parameters. These parameters are nuisance parameters. They are for the prognostic factors. We will be adjusting, of course, or designing in the assumption that we will be adjusting for the prognostic factors, but those will be nuisance parameters. I'll be talking about least squares, but as we mentioned earlier this week, might perfectly well use generalized linear model if the designs should be efficient for generalized linear models if there isn't too much variation in the response. I will be using optimum experimental design. I will be doing what Peter wouldn't do, chose not to do, let's say, which is to do d-optimality. Well, I won't actually be doing d-optimality, but let's start talking about that. So when patient n+1 arrives, we've already allocated the first n patients. So you maximize this determinant by allocating patient n+1 who arrives with a vector of prognostic factors. They will be allocated where this variance is a maximum. This is like the sequential d-optimality in the first talk that we had this morning. We're not actually interested in all of the parameters. We may be interested in linear combinations of the parameters. Here's the set of linear combinations that we might be interested in. Then the DA optimum design is going to minimize this variance covariance matrix here, and then there is a similar kind of thing. This is this quantity here from the equivalence theorem is where sequentially you want to choose the treatment for which this quantity is a maximum. I see I've lost a J there. Okay. So you can calculate this for each potential allocation. Then if you're designing sequentially, you would just allocate the patient for which that variance is a maximum. Here are some linear combinations of parameters. I'm going to be interested in adaptive designs, so I'm going to want to skew the treatment allocation in the favor of what seems to be the best or the better treatments. In general, the special case then of de-optimality, when the number of contrasts that I'm interested in is 1, I'm going to want to minimize the variance of this quantity here. Here are my omegas. For 2 treatments then, I would have an unequal allocation, weight P on the first treatment, 1 minus P or minus 1 minus P on the second, zeros for the nuisance parameters. Then the optimum design will asymptotically allocate a proportion P to treatment 1 and 1 minus P to the other treatment. So you do the same thing with 3 treatments and so on. And in adaptive designs, we will use the data to choose P. So that then is standard ideas on the sequential construction of optimum designs, the design region being the choice of treatment for the next patient, and we could sequentially allocate treatments to give some kind of optimum design measure, minimizing the variance of this linear combination. But that doesn't have anything to do, that ignores the randomization that I want. So here, for example, is one form of sequential adaptive design using optimum design theory. So in the sequential design, as I said, you allocate that treatment for which this variance treatment, the number of patients who've already got the new vector of prognostic factors, is a maximum. One way of generating just a design with some randomization is to allocate the treatments with probabilities proportional to this. But we want to skew things. We don't know these PJs yet, but when we know them, we will want to skew according to those. So if we allocate with probabilities proportional to this, then we will get a design which is, to some extent, optimum, and we'll have some randomization built in. And as I say here and here, the optimum design, all of these quantities, these variances are equal, and the design allocates treatment J with the probability Pj. And in adaptive design, we want the Pj to reflect the desirability of the treatments. And one of the things I'm going to do in this talk is to discuss a few of these rules. More importantly, I want to discuss how I think they should be compared, or I'm going to show how I compare them. So here is a bit of adaptation coming in then. Suppose that large alphas are good, then we can adaptively estimate the skewing proportion by something like this, cumulative normal distribution, and T is a scaling parameter, which if you know what kind of treatment effect you're interested in, and you know what kind of proportion should go to that better treatment, then the T will be determined. So then take P1 equal to this P hat. These alphas are going to be the estimates that we get during the clinical trials. We go along re-estimating after each patient. So you take P1 equals P hat and P2 is 1 minus P hat in the calculation of this probability. And the allocation proportion eventually converges to this. And if there is no difference in treatment, we'd asymptotically get half of the patients on each arm of the trial. Well, what kind of things might you be interested in such a design? How do you know if it's a good one or a bad one? I won't discuss power. Perhaps we should talk. It'd be nice if somebody could make comments on that later on. What I will talk about is the idea of loss. We're interested in a linear combination of the parameters. Suppose we've got a balanced design or we don't have any covariates, then the variance of this linear combination is minimized when the proportion Rj of the patients receiving treatment J is Pj, and the same is true for the design with balance across covariates. And the effect of randomization is slightly to unbalance the trial. When we look at what we've got after the nth patient, the trial on average will not be quite balanced, and the variance of this linear combination will be increased a little bit. So, in that case, then, well, this doesn't matter too much here. What the variance is for the optimum design doesn't depend on p. For other designs, we're going to get this variance here. So the efficiency of a design is this. And instead of thinking about the efficiency, all of the designs that I'm looking about as time goes on become, the efficiency tends to 100%. So that really isn't very informative. Here is the variance. It's sigma squared over n. I define the loss as writing the variance as being sigma squared over n minus some quantity here, because it's going to be bigger than sigma squared over n, so there'll be some positive quantity here to subtract. And perhaps that's on the next slide. Yes, there it is. Good. So the loss due to this randomization over a large number of trials is the number of patients on whom information is lost due to the lack of optimality of the design. So with a random element in the treatment allocation, you've got any trial going along, ln is going to be a random variable. Suppose that it, if you do this, it has an expectation being a random variable, and there are asymptotic results for a few kinds of trials. If you allocate the treatments completely at random, then the loss is Q, where I haven't stressed this. Q is the number of nuisance parameters. So if I got 2 treatments, I got an overall mean, which I'm not interested in. I mean, it's just a treatment difference. That's 1. And I've got, in that case, I'll have 4 prognostic factors. So this is a result mentioned by David Cox at the opening of the conference. A rather more complicated result to obtain is this Q over 5 obtained by Berman for the DA optimum rule that I mentioned above. But if you've got a deterministic design, then of course you allocate always to the larger value of this variance, then the thing will be 100% efficient and there will be no loss at all. So that suggests that removing randomization, of course, reducing randomization decreases the loss. You get better balance, better inferences. However, the reverse to that is bias. So selection bias arises because the clinician can guess which treatment is to be applied next and perhaps allocate accordingly. So we can define bias as the for each n, we can define it as being the expected number of correct guesses minus the expected number of incorrect guesses. So 1 is bad. That means you can guess perfectly well. 0 is the best you can do and be sensible. Of course, you can get that negative values if you make silly guesses. If you always assume you're going to allocate the overrepresented treatment, as it were, then this will be less than 0. And as I say, that does depend on whether sensible guessing is being made. So in my calculations, I'm going to assume the person is making as sensible a guess as they can. All right, so these are the kind of pictures that you get. These are non-adaptive rules. Balanced, P is equal to a half. D is the deterministic rule. The loss goes down very fast. The bias stays at 1 because you can always guess what is going to happen next. A random rule, the loss here, there are 5 nuisance parameters, so the loss is 5. but the bias with the random rule is 0, and other rules doesn't matter very much. Other rules lie in between. This is this DA optimum rule here, and here is a rule using Efron's biased coin. And really the thing is that this works out as you would hope, I think, that here is the order of decreasing randomization, so loss goes down, and here, in the same order, bias goes up. So there is a trade-off. And you can actually plot these two things, one against the other, and decide which rules are admissible and which rules are inadmissible. For example, the Pocock and Simon minimization rule is inadmissible in this sense. You can always do better than that. Okay, the thing that I got sidetracked in when preparing this talk was the idea of regularization. I haven't found much about it in the literature. Perhaps it is well known to people who practice clinical trials, and they could point me in the direction of some literature afterwards, or tell me that I've got it wrong or something. That would be very helpful. So, the point is that some individual adaptive designs can be very unbalanced. Very famous one was, there were several trials, historical trials on ECMO. One of them stopped very early because the allocation rule was very unbalanced. Well, it wasn't the only reason it stopped, but I mean, it made inference very difficult. What I showed you before, what I've talked about are average properties. Well, that's not much use, really. I mean, they're a guide to what's going on, but average properties are not enough because the clinician runs one trial. And the idea of the regularization that I'm going to follow is to ensure that all numbers to each treatment are greater than some limit. So, for example, for 2 treatments, we might allocate evenly for the first 10 patients. Then if nj is less than root n, that treatment is allocated when n is an integer squared. So the first regularization, if n is 800, will occur when n is equal to 36, and the last for 784, and similarly. Don't know why that's not 16 there. Perhaps somebody could tell me. Oh well, here are the 2 treatment then. What is the effect of regularization? What kind of properties do these designs have? Here is a 2 treatment design. I'm going to take the mean difference such that the probability of allocating to the better treatment, which is the first treatment, is 0.75. Here are the average losses for 4 rules. It doesn't matter particularly which they are. The thing to notice is these are the losses. These are averages, and they're much less, well, 2 or 3 patients less for the regularized design than for the unregularized design. Actual detail of one of those pictures, if you look, you can see the effect of the regularization. It causes a slight decrease in loss at each of these points, which are integers squared. These plots are the proportions allocated to the better treatment for each value of n, not how balanced, not the ratio in the whole trial, but for each n, how many patients get allocated over a large number of simulations. These are non-regularized. These funny little blips here, of course, are the effect of the regularization. Some of the trials have got too unbalanced and are being corrected. So treatment 2 is allocated rather than treatment 1. Then, well, there seem to be clear advantages to regularization. It decreases the average loss, but you would think it might increase the bias, because if the trial is very unbiased, you know what is going to be allocated next. I couldn't detect this. I think the point is that the actual ratio R is so the change is so small that it doesn't show up. But we shall now look at individual trials, and here we go. Here, for example, is loss, and you can see what is happening, I think, quite clearly. There are quite a lot, in the early stages, well, at the early stages of the trial, there are quite a lot of patients get allocated, quite a lot of trials have relatively large values of loss here, far fewer here. And this is caused by unbalanced trials. You can see this, these are the ratios of these are the ratios of the total ratios over the whole trial so far, and you can see up here there are quite a lot of rather extreme designs, whereas our target allocation was where was it? Down here. So this is the effect of the regularization. You can't have trials that are that unbalanced. Thank you. Well, we can do the same thing with designs maximizing utility with other ways of adaptively finding the P. So this is a utility calculation, two parts of the utility, one of which is providing estimates with low variance, the other provides randomization. If you work at it and maximize that utility, you eventually get to an allocation rule, which is rather similar to the arbitrary one I had before, except there's an extra parameter here and there's 1 plus the variances rather than the variances. These are quite interesting rules because for small trials, they drive the thing towards balance. For larger things, they tend towards being random. And these are just finding the target probabilities. Let's see what we get next. Okay. So I simulated some of these trials, and Sandra, for example, has already mentioned the point that the designs may be fine, but what really are the inferential properties of the quantities that you get out of such a sequential procedure? Well, believe me, I simulated a trial and so on, and here we are. This is what, well, for an adaptive trial to work, you have to have an effect, but I'm interested in sort of the null distribution of the test statistic, so I have to take the non-centrality parameter off again to see what I've got. Here are some results. This is a t-test for treatment equality. Here are box plots from 1,000 simulations. Here is what you get when n is equal to 50. So it seems perhaps 50 is too large a number for these effects to show. But it seems as if in this particular inference anyway, you don't, Henry mentioned this too, you don't have to worry about the effect of the sequence of the adaptive design on the inference. I think, yeah, that's it, isn't it? That's well, I've managed to get through all that. That's quite amazing. I hope a few words were audible and comprehensible. Thank you very much.
Please.
Seems to me that a way of avoiding the problem that you had to fix by regularization would be to include interactions between the treatment and the covariates in your model. And that way, they're not nuisance parameters so much anymore because you actually could observe different people having different probabilities, and that would matter in the projective function. So that would force more balance into your design.
Okay. I'll believe you. I don't quite at the moment see why, but so the idea was to actually include interactions between treatments and covariates. And yes, of course.
You thought about that. I don't know if the people here understand. Dr. Atkinson has addressed one of the hardest problems in adaptive randomization, which is to favor the better treatment, but also balance on covariates. It's quite an accomplishment. But we've put in treatment covariate interactions. And the one thing is that you must have a much larger sample to get at those extra parameters. So it makes it a much more difficult problem. But that doesn't solve the problem. The thing that we noticed was that we call what he calls regularization, we call a burn-in. You do a 50-50 randomization, for example, for an initial run of patients. because you don't know enough and your statistic is very, very variable, you have a very high probability that you'll imbalance in the wrong direction. That's what regularization gets rid of.
Yeah, I do have some simulations. I'm sure you're all dying to see them of 3 treatment effects. And they are much, well, the ones I've looked at are much more likely to head off in the wrong direction. It really, yes.
Andrew?
Can you show us your last slide, the one before this? Yes.
That's it, isn't it? Yes.
Beautiful line.
It's nice, isn't it? Yes.
Well, I was wondering, your test statistic is really difference between 2 estimates divided by something else, variance.
Well, that's right. No.
So those 2 estimates are the maximum likelihood estimates, because in that case I'm not surprised about your result.
Well, they're least squares, so the answer is yes, isn't it?
Well, there is a theorem that says in that case, whatever the design, the maximum likelihood estimates would be normal.
Oh, okay.
So I think that's it, possibly.
But they would have exactly the same. They would have exactly the same distribution as if you hadn't done a
Well, the
adaptive design. Is that what
No,
you're saying?
it's-
No.
normal, yes, in that sense, yes, normal.
No,
But
oh, okay.
with a different variance. But I think you divide by the right variance anyway. So.
Ah.
Well, this is what I gather from your paper.
Yes.
So,
yes, okay.
That,
So that's what your theorem is saying, is it? Is your
it's
theorem?
not my theorem, it's a theorem, yes.
Whose theorem?
Well, I think Rosenberger was the first one to prove it
Oh,
under certain conditions, and then
Who, perhaps, or somebody? Yes.
and we proved it as well in the paper that you
Yeah,
kind
that's right.
quoted.
Mhm.
Yes.
Okay. Well, this is all wonderful. So.
More questions? We could have a question for Peter. You have a minute.
Question from Peter. I thought this was going to be. Was it?
It's a question
Or
for
pizza, yeah.
Yes, Ben.
Patients arrive sequentially as helped here, but so how does that impact on your 2-stage process where you patients, the early patients maybe finish the first, may have reached T1 before you've even got other patients onto that, and then tumour growth may step up again while they're waiting to be allocated to the second stage. How does that affect it?
Good comment, and that also gets a little bit to this talk, right? So for the random discontinuation, the fact that patients don't arrive all simultaneously does not create a problem, because it's one upfront. It's an upfront optimal decision that we set the T1, T2, and the N.
But does that not mean that some patients will wait longer between the first and the second stage?
Yeah, of course, not longer, but I mean they'll get randomized later. Not all patients get randomized at the same time. Same answer in different words. Time is relative for the patient. It's not calendar time. You said here the thing is sequential. Of course, it's sequential in the sense of being myopic. At each time, you find the best one.
Yes.
And that occurred. That's a recurring theme, I think, in many talks.
Yes,
Do you have a
yeah.
notion of how much you lose or might win by going like fully sequential or somewhere towards that goal?
No. You mean I should? What is the stuff called? You mean dynamic programming? Work myself back from the end, or?
It's nirvana, but there are
Yeah. Yes, that's right. Yes. Okay.
Okay. Fun continues after lunch. But for the moment, let's thank both speakers and all gathered.